So following on from the previous video, I asked you to sketch this function here, and then we got to this stage here where we know this point, we know this point, we know this, and we know this. So now we need to consider looking at this function here. We need to consider where the gradient will be 0. Okay, so to do that, we need to differentiate this. Okay, so when you differentiate it, hang on. So starting with your function here, differentiate it. So remember, we've got to differentiate this e to the power of this thing here. So remember, to differentiate this, just remember that when you have e to the power of x, if you differentiate this, it will give you this. If you differentiate e to the power of 2x, it will give you this. Now what? So you've got this thing here. Imagine this as being, imagine u as being u equals 4 over x. So when you differentiate this, it will become, well, you can imagine as being a 1 here. 1 moves down here. So basically, when you differentiate this, it will give you this. But then because u is a function of x, you've got to multiply it with. So it's you using the chain rule here. Okay. So imagine this as being a u here. So when you differentiate this, well, the coefficient goes down, which is 1, which basically is the same thing. Okay, and then you've got to differentiate the u. Well, differentiating the u, differentiating the u. So rewrite the u. So remember that this is u here. We've got to times it with. Well, we've got to differentiate this u here. So imagine the u as being this, and rewrite it as this. So when you differentiate this gets moved down to here, so it will give you minus 4, and then the power itself gets minus by 1, so it will be this. Turn it back into this, so it will be 4 minus 4 times 1 over x squared, and then the minus 4 gets multiplied to the top. Basically, this bit here will become this. Okay, so when you differentiate it, it will become this. Okay, and don't forget u. Earlier u was 4 over x. So when you tidy this up, this gets multiplied to the top. Okay, so hang on, let's start again here. Our job was to differentiate this here. Our job was to differentiate this. Okay, so imagine this as being like a bubble here. When you differentiate that, it will blah blah blah. It will give you this. Okay, and then you got to. We want to know where the graph will have a gradient of 0. So let's set this to be 0 here. So imagine this as being one bubble here, times both sides by x squared. That will then give you this, and then well, do whatever you want here, but imagine this as being a negative block here. So add this block to both sides. This will then give you this. Well, blah blah blah. So looking at this here, if you look at the graph of y equals e to the power of x, it looks like this. Okay. So imagine this as being imagine you're looking at a graph of y equals e to the power of x. Apart from x being dead on 0, because it would break down here, everything else is positive. Everything else is positive. You're never going to reach 0 unless you head towards infinity. Well, the point is that at no point on the line is the gradient 0. Okay, so there's no point where the gradient will be 0. If you head towards negative infinity, then the gradient will be flat, but it will never be 0. The gradient will be near 0, but it will never be 0. The point here is that looking at this derivative here, there's no point on that. There's no point where the gradient will be 0. So hang on. So looking at this here, no. So we know the graph would do something like this and heading towards 1. This is really big, heading towards here. But at no point will the gradient be 0. So we now need to look at the interval now. So looking at the interval, it turns out to be negative on this side and negative on this side between here and here. Okay, but let me show you why this is negative and this is negative. So looking at our derivative, so this is our derivative here. When x is in the negative realm, okay, when x is in the negative realm, this here will always be positive. Okay, so this here will be positive, and then this here will be well, if you look at the graph of y equals e to the power of x, apart from x being dead on 0, because we are considering anything else apart from 0 on the negative side. So this thing here will be well, looking at the graph here, it's always positive. But then you're timesing a negative number here, so really overall, when x is over on this side, it will be the gradient will be negative. Okay, meaning that the graph, if the gradient is always negative, then the graph has to be going downhill all the time. Okay, it has to be going downhill. And then looking on this side here, looking at it when x is in the positive realm here, apart from x being dead on 0. So looking at x being greater than 0, this here will be positive, and then this here, well, if you look at the graph of y equals e to the power of x, this is always positive here. This is always positive, and then you're timesing a negative. So overall, it will be a negative. Okay, overall it will be a negative. That's why this is a negative, meaning that, well, if the gradient's negative, then from here it should always be going downhill. The original function should always be going downhill, downhill, downhill. So it seems to be like this. Okay. So now we need to consider the concavity. So we need to look at the second derivative. I will continue in the next video. Okay.